Section 1 starts off with a pretty basic question, and that question is, what is statistics? So, just to get an example here to get started, let's consider this case here where we have got some numbers here. These represent the annual wages in thousands of employees at this place called S-Mart. So you can see you got some employees making $30,000 a year, a couple making $40,000, one making $150,000. And let's say these employees go on strike. You've got the smallest union in the world, but they go on strike over wages, and both the union rep and the business owner are asked by the local news media what the average pay is at S-Mart. You've got a couple responses. The union rep says the average pay is $30,000 per year. The business owner says the average pay is $50,000 per year. So these sound completely different. So the question is someone lying? So what do you think? Is someone lying? Are they both lying? Can they both be telling the truth and get totally different numbers like that? Well, what some of you may be thinking is that maybe they're talking about different averages. So there's a word we have to be kind of careful about. Average. This word average can mean a lot of things. There really are about 14 different ways to calculate an average, and they could all be used here. Now there's 3 of them that you typically learn about in school. They, at some point in high school or college, you'll hear about ways of taking averages, and the 3 that come up, they always start with an M. What do you think they are? Mean, median, mode, right? You always hear about those, the mean, the median, and the mode. Well, 2 of those are used all the time. That's the mean and the median. The mode really is hardly ever used, but it always comes up. So we'll look at these in more detail later on, but just to get an idea, can you think about using the mean, median, or mode? How could you come up with an average of 30,000 using these numbers? And that would allow you to say the average pay is 30,000 a year. Well, if you think about the mean, median, and the mode. Okay, mode, that's one that comes up the most, right? So if we look at these numbers here, the mode here is 30, right? $30,000 a year, that's the mode. Again, the mode is not really used a lot, but if you were going to use it here, you could. I mean, the mode is 30,000, so typically that one's not used. But what about the median? Do you remember what the median is? If you're, you write these down here. So, like I said, we will talk about these in a lot more detail later. But there's the mean, the median, and the mode. We actually will study 5 different ways to calculate averages. These are 3 of them. And we look at weighted means and trimmed means also later. But there's about 12 or 14 different ways to calculate averages, like I said. But the 2 that you see the most are the mean and the median. And there are times when you should and shouldn't use both of these. So for right now, the median, that is where if you line up all the numbers in a row, the median is right in the middle. These are lined up, right? Lined up in a row, meaning from smallest to largest. So they're lined up from smallest to largest. So this is the number in the middle. So the mode here, the median here is 30,000. So if you say the average pay is 30,000 a year, it's technically true if you use the median. Now, I'll tell you that typically when money is involved, you do use the median for reasons that we'll see later. But the median is typically not affected by outliers where the mean is. So the mean Many of you will remember when you find the mean, you add up all the numbers and divide by how many there are. And if you add up all of these numbers and divide by 1, 2, 3, 4, 5, 6, 7, divide by 7, you end up getting this number 50, which represents 50,000. So that number is the mean. So both of these statements are technically true, right? They're both technically true. So nobody is lying, but you could say maybe one of them is a better number in this case. Like you could say, well, maybe, although no one is lying, it could be a little misleading to say the average pays $50,000 a year, because really only one person makes that much. So if we're using average to mean like a typical number, it's not a very good number to represent a typical number in this case. Although technically it is true, the mean pay is $50,000 a year, so you could say the average pay is $50,000 a year. But this number would be better in this case because it represents more of like a typical number here. So they're both technically true. So nobody's lying here. There would be times when you want to use the median, sometimes when you want to use the mean. But we just have to be aware that if somebody's trying to convince you of an idea or convince you to buy a product, you have to really pay attention to what you're being told. You could be being told something that's absolutely true, but it's absolutely misleading. And this happens constantly. It happens daily on the news. It happens all the time with politicians because they're trying to convince you of an idea. So we just have to be aware of it. And it's even worse now because it used to be, especially in politics, you just had to be sort of clever in how you spoke so you could be saying things that were technically true but maybe supported your cause. But now it seems you can just say anything you want. It's kind of unusual. We're in unusual times now. But anyway, this is a really easy idea where you can see these numbers are totally different and they're both true statements. So we just have to be careful. We have to understand statistics so that we have a good understanding of what's happening in the world and we're not easily misled. So because of that, there's a debate that's starting in schools, and there's maybe a transition coming. So in most schools right now, the highest math class you can take is calculus, and there are classes that will lead you up there. You'll have algebra and then trig and then maybe pre-calculus and then calculus. Well, there's a push right now to switch that so that statistics is the top class. And the reason is because of the fact that in the world we live in today with big data, tons of data, there's real-time analysis, there's risk and reward that we have to be aware of, and statistics better handles that. So for the average person, the thinking is maybe we should have this be the class that everybody shoots for. And this one will still be there because calculus, we need calculus for the STEM fields and for engineering and things like that. So this will still be there, but we kind of like shift the focus so we're aiming the majority of people towards statistics. So it's sort of a push. So these pushes take a while to happen, but it may happen. It may happen. Maybe when your kids are in school, statistics will be the top class. And I've got a video here from Arthur Benjamin. It's a TED Talk, but it's a real short one, and he makes a pretty good case. So I'm going to play this for you guys so you can see what you think about it.
President Obama invited me to be the next czar of mathematics, then I would have a suggestion for him that I think would vastly improve the mathematics education in this country. And it would be easy to implement and inexpensive. The mathematics curriculum that we have is based on a foundation of arithmetic and algebra, and everything we learn after that is building up towards one subject. And at the top of that pyramid, it's calculus. And I'm here to say that I think that that is the wrong summit of the pyramid. That the correct summit that all of our students, every high school graduate should know, should be statistics, probability, and statistics. I mean, don't get me wrong, calculus is an important subject. It's one of the great products of the human mind. The laws of nature are written in the language of calculus. And every student who studies math, science, engineering, economics, they should definitely learn calculus by the end of their freshman year of college. But I'm here to say, as a professor of mathematics, that very few people actually use calculus in a conscious, meaningful way in their day-to-day lives. On the other hand, statistics, that's a subject that you could and should use on a daily basis, right? It's risk, it's reward, it's randomness, it's understanding data. I think if our students, if our high school students, if all of the American citizens knew about probability and statistics, we wouldn't be in the economic mess that we're in today. Not only that, if it's taught properly, it can be a lot of fun. I mean, probability and statistics, it's the mathematics of games and gambling. It's analyzing trends. It's predicting the future. Look, the world has changed from analog to digital. And it's time for our mathematics curriculum to change from analog to digital, from the more classical continuous mathematics to the more modern discrete mathematics, the mathematics of uncertainty, of randomness, of data, in that being probability and statistics. In summary, instead of our students learning about the techniques of calculus, I think it would be far more significant if all of them knew what 2 standard deviations from the mean means, and I mean it. Thank you very much.
So in the coming years, we may see that transition start to happen in the schools. But one more thing we should talk about before we really get started here. Just want to give you a little bit of background about statistics. So to compare statistics to some other areas of math you've heard of, let's compare it to, say, geometry. And I'm not going to ask you about this on a test or a quiz. I just want you to have some idea of what we're dealing with here, because statistics is very new when you compare it to these other branches of math. So geometry, we can trace this back to Egypt. And they use what we would call practical geometry. This is as far back as 3000 BC. So, 5,000 years ago, there was an understanding of all the basic shapes and areas and volumes, geometric figures that were used for determining boundaries of properties and things like that. So this is 3000 BC, and it has not changed. There have been no changes in this sort of geometry. The area of a square is still x squared. So if x is the length of a side. Then the Greeks, we could talk about Euclidean geometry. And this was, there was a book published in about 300 BC. 300 BC, there's a book called The Elements, that you may have heard of. The Elements was published by Euclid, and it has been published routinely ever since then. There's been over 1,000 editions. And in fact, there's only one book that's been published more often than Euclid. Only one book on the planet. You know which one that is? It would be the Bible. It's the only one with more editions than the Elements. In fact, if you studied math up until around the year 1900, you would have read the Elements. That would have been part of your training in studying mathematics. And since then, there have been some other many other geometry textbooks published, and a lot of them even that you studied in high school. A lot of you took 10th grade geometry, and that was still based on the elements, the 2-column proofs and things like that. So the point is, though, that if you go way back to these times, we are still using these same principles of geometry. It has not changed. Now, there's been other sorts of geometry. So that what we're talking about basically here is Euclidean geometry, and there are non-Euclidean geometries and different topologies that are studied, but the basic Euclidean geometry has not changed. So the book you studied in high school wouldn't have changed a whole lot from this one back here, 300 BC. So it's geometry is well established, not any big changes. Even calculus. I teach calculus, and the book that we use has theorems that haven't really changed too much in the past 300 years or so. So even calculus has had, at least at the basic level, there have been not too many changes. It sort of got all pieced together roughly 300 years ago or so. And the theorems that we look at are the same theorems you would have seen in a book 100 years ago. Now, all of that is completely different when it comes to statistics. Statistics is a much newer subject, and it's still changing. There are things that are not settled yet in statistics. So when I was a student, I took the same class that you're taking right now. This is a first-year statistics class, and I even had the same author in the textbook I had, but I had the second edition, where now we have the 12th edition. And the things that we did in statistics in the second edition are different because we can use better techniques now because we have graphing calculators. And without a graphing calculator, you're forced to use tables. So they lack a certain amount of precision that allows you to do more. That now we can do more with the graphing calculator. So certain techniques are changed. Because if you don't have this graphing calculator, you have to do your calculations differently. So sometimes you need an entirely different technique. So it's changing. So just to give you some background here, see how new this is. Again, I'm not going to ask you about this. It's just so we can see where we're at. The thing I need you to understand about statistics is it's new, it's fluid, it's changing. And it's changing even right now. There are disagreements. There are certain things that are not dialed in. And so in different fields, you do things a little differently. So it's something you'll notice. I just want you to be aware of it. So probability. It wasn't studied a whole lot until about the 1650s. And even then, it was only certain things were studied, and it was driven by gambling. So they're professional gamblers who started asking mathematicians questions about dice games and card games. And that was really the driving force for the subject of probability. And there wasn't a whole lot of advancement for a while other than just answering particular questions about card games and dice games. So modern statistics this started to be developed in the late 1800s. Like a lot of it was like around in the 1890s, so not that long ago. And to really understand statistics, you have to first understand probability. So when this started happening, then there was some more discussion of probability, and it went away from just the ad hoc methods developed for gambling, but into more general methods that could be used in statistics. And then there's some advancement here. And then the undergrad stats that we study, and pretty much that everybody studies in college, these were mostly developed in in the 1930s. So again, it's fairly new. That's one thing. So this is the the statistics that our book covers, and that pretty much any stats book that you look at would cover. Now, the 1930s. Think about computer technology in the 1930s. Not so good, right? So a lot of the techniques that were developed were not the best techniques, but they were the best practical techniques. If you don't have a computer, there's certain techniques that you're just not going to be able to do. So because of that, as computers developed more, some of these methods changed, and they're still changing. As we develop more counting methods where you don't have to use just brute force counting, but where you can use computers to help you, then the techniques change, and they are still changing. So that's where we're at. So these were developed mostly in the 1930s, and they're still changing. So just keep in mind there will be changes. If your kids take statistics and you help them with their homework, assuming you remember everything that you learned this semester, I can promise you there will be changes, because they're just, like I said, there are techniques that are still being debated and still not quite established yet. So I've got this life table here, and this is a very depressing looking life table. This is from 1662, and John Grant published the book, and a lot of historians credit this as being the beginning of statistics. So this is 1662, and John Grant used some basic statistical methods to estimate birth rate, death rate, and the population of London. So to see what this means, this is pretty depressing. Like I said, if you count up these numbers right here, you get to 60. So what that means is, of 100 people who were born in this era, 60 of them died before the age of 16. So they didn't have a lot of the things that we have right now. Access to clean water, which we pretty much take for granted, that's a pretty modern miracle, actually. So access to clean water was very difficult to come by, and that makes a big difference in life expectancy. Also, there were things, antibiotics didn't really come out until the late 1950s, penicillin. So if you had a plague that could have been a bacterial plague, there was just nothing to fight it. So no antibiotics, vaccines. There used to be just some terrible childhood killers like smallpox, polio, measles, mumps, rubella. Parents for thousands of years worried about these kind of things, and vaccines pretty much took them away. So that's why our life tables are not so depressing anymore. So look at this. For every 100 births, approximately one person made it to the grand age of 76. And this is pretty much the history of the earth until modern times. It was always very difficult to be a human, and most people estimate the life expectancy for most of the time on earth for humans was somewhere between 30 and 35, and it was usually a pretty rough life. Now, it doesn't mean there weren't old people. It just means that it was really fairly difficult to survive childhood, as you can see here. 60 people out of 100 would be dead before 100, or before 16. So we're going to look at a modern life table, which is much happier. So in modern times, the life table that we have is from 2008, and in those times, 66 out of 100 people, which is still roughly the same today. So today, close to 70 people out of 100 can expect to make it to the age of 76. So life expectancy, just to put some things in perspective, life expectancy in the United States in 1900, life expectancy was roughly 47 years. Again, it doesn't mean there weren't old people. It just means that a lot of people died young because of a a lot of terrible diseases that we had to deal with. And again, clean water, things like that. But now the life expectancy is roughly 79 or so. So what we're going to do is see a modern life table, which we've got right below here. And the way this works, really what you need to do is look at your age over on the left. So you find your age over here, and then if you follow over here, this is your expected, your average, meaning the mean in this case, amount of years you should expect to live if you are in this age group. So find your number, and then I have some good news for half of you and some bad news for half of you. So if you look over here, so like let's say you're 21. So you look over here, so don't read it like, what? I'm only going to live to 58? That's not what it means. It means you've got 58 more years left at this point. Okay, so that's average. So once you find that, you got good news and bad news. Okay. Ladies, good news for you. This is a composite table, so it means it's the ages of men and women. And women generally live longer. So ladies, if you look at your number, add 1 or 2 years onto your number. And then for the guys, bad news. When you look at your number, take away 1 or 2 years. But even with that, living in modern times is a much happier looking life table. Okay, so that's just wanted to get us away from that sad life table and look at a more modern one. And what we will do at this point, finally what you've been waiting for, we will actually take a look at the section 1.1. I just wanted to give you guys an understanding of where statistics is. It's new, it's changing. There are a lot of disagreements among statisticians and researchers about how to do things. But we're going to look at the basic first year stats class. So the first couple of chapters, unfortunately, there's just a lot of definitions, and we just have to get through these. Okay, so statistics is more interesting than it's going to seem at first because we're going to go through all these definitions. So just kind of bear with me a little bit, and let's get through these. So here is a definition that our authors use in our textbook, and they define statistics this way. They define it as a study of how to collect, organize, analyze, and interpret numerical information from data. And why do we study statistics? To make, this is one reason you could say, to make more effective decisions. Okay, and there are a couple branches of statistics that we're going to study, and pretty much everybody studies these. There are descriptive statistics. Okay, so descriptive statistics, this is what we look at first, chapters 2, 3, and 9. And this involves methods of organizing, picturing, and summarizing. Information from samples or populations. And descriptive statistics is easier for sure. It's definitely easier. To me, it seems less interesting, but it's making graphs and charts, talking about mean, median, and mode. And it's easier to do, so it's typically covered first in the stats class. So descriptive statistics, we're describing a data set. The more interesting part of statistics, and definitely a little more challenging, is inferential statistics. And this is really why we study statistics. This is starting in chapter 4. And this involves methods of using information from a sample to draw conclusions about the population. So this is where you look at a sample. All you have is a sample of data, and then you try to infer information about the population that the sample came from. Okay, so we'll start off with descriptive. We'll move to inferential statistics. And this class starts off pretty basic, so be careful about that. It starts off with descriptive statistics, which many of you are familiar with just from previous classes and just from being alive on the planet, and you run into some of this stuff. So students sometimes think, oh, this class is pretty easy. I don't really need to do the homework or do anything. Then all of a sudden you get into chapter 4, and there's permutations and combinations and everything changes. So it's best just to get a good habit, stay right on top of the homework, even if it's, stuff that seems familiar. Stay right on top of it in these chapters, and then we'll move on to inferential statistics, and you'll won't really notice a big change. Okay, so in using statistics, we typically know only the results of a sample. The central problem is to describe the sample, which is that descriptive statistics we just talked about, and to draw conclusions about the population based on the sample results. And that is inferential statistics. So it's just a little paragraph summarizing the two that we just mentioned. And sometimes people say, why wouldn't you just use the entire population? We'll talk about that, but typically you either can't, or it's extremely expensive or difficult, so we will use a sample. We'll look at the sample and try to infer things about the population. But before we do that, we have to gather data. So in order to gather data, we need to be able to know what we're talking about here. So the individual, this is the people or objects included in the study. Those are the individuals. So if you are studying, let's say you want to figure out the average age or the mean age of a GRCC student, well, the individuals would be all the GRCC students, right? Those are the individuals. Then the variable, this is a characteristic of the individual to be measured counted or observed. It's basically the thing that we're going to measure. So if we were trying to figure out the average age or the mean age of GRCC students, the individuals would be the students, the variables would be the students' ages, right? That's the thing that we'd be measuring. Okay, so as an example, see what we've got here. So we'll find out why later, but often if you are studying human populations, you want to divide them by gender. So you have either all males or all females. We'll see why later, but for this example, let's say we've got some individuals and they are female GRCC students, and here are some possible variables. And remember, these could be pretty much anything that you can measure or count. So variables could be the height of individuals, could be the weight, could be the age, could be the nationality, And it could be the eye color. Okay, and variables can be quantitative or qualitative. Quantitative or qualitative. And we have to know because they require different sorts of mathematics, so we need to know which one we're using. So a quantitative variable, this is one that has a value or numerical measurement for which operations such as addition or averaging make sense. And when you think of averaging, think of the mean, not the mode. Think of, would it make sense to say what is the mean? If it does, then it'd be a quantitative variable. So if you're trying to figure out the average age of a student's car, you could definitely find the mean age of a car, right? What about the mean make of a car or the mean color of a car? Those wouldn't make sense, right? So they wouldn't be a quantitative variable. So if you have a numerical measurement and taking an average would make sense, then you've got a quantitative variable. Okay, qualitative variable, which our book will use this phrase qualitative variable, but many other books will call it a categorical variable. Okay, so qualitative or categorical means the same thing. A qualitative variable, this describes an individual by placing the individual into a category or group, such as male or female. Okay, so for us, we've got quantitative and qualitative variables. And let's see, we've got a little note here. And the note says this. The note says, later we will see that quantitative variables are either discrete or continuous. Okay, you guys still with me? It seems a little strange for me, the online portion, because I can't see you guys. I can't see if I'm losing you. I can't throw in any of my horrible jokes to keep you awake. So try to do what you can to stay awake. It's not going to be. It's harder to hold your attention when we're in this sort of environment online, but guess we'll have to try to make the best of it. So, okay, in example 2 above, what we typically do in class is this is where you would get to meet who you're sitting with, which always makes things a little easier to keep us animated and keep active and awake and alert. So, can't really do it this time, but in example 2 above, what we want to do is write qualitative or quantitative next to each variable depending on which type of variable is shown. So up here we want to write, next to each one of these, we want to write either qualitative or quantitative for these variables right here. So in other words, looking at height, quantitative or qualitative? Quantitative, would it make sense to say what's the average height of a female GRCC student? And it would, right? Height would be just fine. So this would be a quantitative. So just take a second, press pause, and fill in the rest of them what you think, and then check back and let's see what you got. Okay, hopefully you pressed pause. Hope you're not just waiting for me to do it. So weight, average weight, that makes sense. That's quantitative also, right? Quantitative. Age, we could talk about the mean age. That would make sense. That's definitely quantitative. Nationality, could you talk about the mean nationality? All right. That's not going to make sense. That's going to have to be qualitative. Right, that's a qualitative variable. And what about eye color? Mean eye color doesn't make any sense either, right? How could you add up like 17 brown-eyed students, 5 blue-eyed students, green-eyed students? It doesn't make any sense, right? So eye color is going to have to also be qualitative. Okay, so those are individuals. Those are the things that we're measuring, or the variables are the things that we're measuring from the individuals, and they can be quantitative or qualitative. Remember the other word for qualitative? Categorical, right? Our book uses qualitative. Many books use categorical. They mean the same. Okay, so that brings us down to some more definitions. And this one's gonna throw you off a little, maybe, because our book uses kind of an unusual definition for population. And a lot of times when, as I told you, there's a lot of things that are not written in stone. There's a lot of things that are not settled yet. There's open questions in statistics. So many times they'll say, this is how our book does it, and there's these other ways that you can do it, and any of them are fine. But in this case, for population, we have to use our book's definition because it's gonna come up later. So we just have to kind of go with our author's definition for population. So here's how our book defines it. Our book says the population is the set of all measurements or observations of interest. Okay, so the one thing that you might notice is it's the measurements, right? The measurements or observations of interest, not the individuals. So then a sample is just a subset of this group, a subset of the population. So a couple of notes here. First note is population and sample are usually not defined this way. Okay, so just kind of be aware that our book, I have seen other textbooks do this, but most of them definitely don't. So it'll be more clear what I'm talking about when we actually do an example. But the other note sort of describes what our authors do. So I'll just say our authors. We have Brace. It's Brace and Brace are two authors. And our authors mention both the individual and here's the other thing that is typically not done, and the variable when describing population or sample. Okay, so our author is going to mention the individual and the variable, both. Okay, a lot of times if you took AP Stats, you probably defined population just mentioning the individual. But our author's a little different, so the answers in the back of the book are going to reflect that. The individual and also the variable will be mentioned when we describe a population or sample. So here's an example that will hopefully make it clear. So suppose we want to find the mean age of a GRCC student, and what we do is we interview 200 students. And we'll talk about how to choose these 200 students later, but basically we randomly select 200 students. So here is the sample. The sample for this situation, that's the sample for this example, example 3, would be, now it's not 200 students, it's the ages of 200 students, right? The way our author does it, it would be the ages of 200 GRCC students. Okay, so this is the sample the way our book defines it. The way most books answer this question, they would say 200 GRCC students. Most books, when they define the sample, they just talk about the individuals of the sample. And the sample, the way they would say it, is 200 GRCC students. But our authors are very particular about sample and population. Our authors say, also, tell me what you're measuring. What are we measuring? Student height? No. Student GPA? No. We're measuring their ages, so we need this. So the sample is the ages of 200 GRCC students. Now the population is going to be just like this, but it's not of just 200 students. It's of all the students. So look how when I write this, what it looks like. The population... Oops, I don't know what just happened there. Let me try this again. The population is the ages of, not 200, all GRCC students. Okay, and here's what we have to get used to, and here's what's going to be a little different. In both cases, look what we did. For the sample and the population, we mentioned the variable, right? Okay, that's the part that you may have to get used to if you've taken statistics before. For our sample and population, we need to mention the variable. And then here are the individuals. A lot of times, this is all you would have to mention. But for our book, they want us to mention the variable and the individuals. And then here's the key. Right here, we've got 200 for the sample, all for the population. That is really the only difference here. The only difference between these two is for the sample. Remember, the sample is a subset of the population. So the population is the thing we're measuring on every GRCC student. What are we measuring? The age. So the population is the ages of all GRCC students. And the sample is a little subset of that, and that is the ages of these 200 GRCC students. Okay, so that's a little confusing sometimes because the definition's a little different for our book. All right. We'll practice a couple more too. Then we come to the data are versus data is controversy. I didn't know this was so controversial until I started teaching this class, and I think it was a take-home quiz we had, and there was one of the questions said something, it's just writing. There's a sentence and it says something like data are, and then it kept on going. And this student was very angry about this, and I still remember this. She crossed this out and she wrote in all caps. That's how important it was. Data is. Very excited about this. Like, don't say data are, it's data is. Okay, so you actually can say this however you want to. Now, you notice that in most math books, including ours, most of them will consider this. They'll think of it like data. They'll think of that as plural. And they'll say, well, datum datum really is a singular, data is plural. When you hear it, if you think of datas, even though nobody says it, it'll sound better. But in technical fields, we typically, the way people will read data is they'll think of it as plural, so they'll say data are. Now, in other fields that are not technical, they'll be more interested in how it sounds. Like sometimes technical people are more interested in being consistent. So they're going to say data are. Our book will always say data are. But in everyday writing, people will typically say data is. So if you are on Team Data R, you can cite the APA Style Guide, which will say data are. But if you are on Team Data is, you have a powerful ally on your side also. I think it's the other one. I can't remember exactly, but MLA guide, I think. I think the MLA guy says that either one are okay. So they're both fine. Use whichever one you want. In most technical areas, in most technical people, you'll see the phrase data are. In everyday speech, you'll typically see data is. Either one is fine. But right now, I wish I could see you guys. I'd say how many people are already on Team Data R. And usually only one or two raise their hand. Then I say data is. Everybody's on Team Data is. So by the end of the semester, it's my job to convert you to Data R. You got to get you on the right team. Team Data R. That's my goal. By the end of the semester, you'll say data are and you'll say, yeah, sounds good. And you'll say data is. Who would ever say data is? That's the goal. But, and you can use however you want. They are both perfectly fine. Okay, moving on to more definitions. Population parameter and sample statistic. Okay, a population parameter is a numerical measure that describes some aspect of a population. So an example here would be like the mean mu, Greek letter mu, looks kind of like a cursive U, but it has a little branch on the left also. Mean mu is a population parameter. So when you see this symbol, mu, it means mean, but it also more specifically means mean of a population. It's a population parameter. Okay, a sample statistic is a numerical measure that describes some aspect of a what? Sample. And an example of that would be mean X bar is a sample statistic. Okay, so when you see this symbol, again, it means it's a mean, but more specifically, it's a mean of a sample. Okay, and then the easy way to remember this is parameter starts with a P, population parameter, sample statistic. The reason that I mention this is because sometimes you're just going to see this word parameter, and we have to know that parameter came from a population. And sometimes you just see this word statistic. We need to know that it came from a sample. So sample statistic, population parameter. Okay, and there's just an easy example of them. We'll see more. Also, there's a little note here we need to know. The note just says this. This note says that Sample statistics may vary from sample to sample. So they may vary, and they usually will vary from sample to sample. Okay, but population parameters are fixed for a given population, so they don't change. Okay, so for instance, let's say, let me make a little room here. So let's just make some room. Let's say we've got a population here. Let's say this population has a whole bunch of numbers in it. All these, just a whole bunch of numbers. Every number represents the age of a GRCC student. So there's thousands of these numbers. Well, if you went to the registrar's office and said, what is the mean age of a GRCC student right now at this instant in time, they could give you a number, right? Let's say it's 27.8. It's the mean age of a GRCC student. Well, typically we don't know that. Typically we don't have access to this population. So what we will typically do is, out of here we will take a sample. So let's see, we each got a sample of 100 students chosen randomly, and I take the mean of my sample. Let's say I get 27.1. And then what if somebody else takes a sample of 100 students and they get 26.4? Should we be shocked that these are different? We shouldn't be, right? Because these are samples. There's going to be variation in the samples. So that's what they're saying. Sample statistics may vary from sample to sample, but the population parameter, this is going to be fixed for a given population. Okay, so that's what they're talking about. So let's take a look at page 11, number 8. You've got this problem right over here. Page 11, number 8, just in case you don't have your book yet. Here is the problem. It says, what is the average miles per gallon for all new hybrid small cars? And it mentions that using Consumer Reports, a random sample of such vehicles gave an average of 35.7 miles per gallon. So step 1 says identify the variable. So the variable, this is the thing that we're going to measure, right? The variable is this thing that we're going to measure. So it is a characteristic of the individual to be measured, counted, or observed. The thing that we're measuring here. Well, in this case, the thing we're measuring is miles per gallon, right? So identify the variable. That would be miles per gallon, right? Thing we're measuring. And is the variable quantitative or qualitative? Well, remember we've got quantitative or qualitative. What's the other word for qualitative? Categorical, right? So quantitative means that talking about the mean would actually make sense. And it would here, right? The mean color of a car wouldn't make sense, but the mean miles per gallon rating would. So it's going to be quantitative, right? Okay, so this part, what is the implied population? So the book always uses this phrase, implied population. They're saying, what's the population implied in this problem? So remember, population, let me tell you what the answer is not. The answer is not all new hybrid small cars, right? Remember how our author defines it, how we have to define it in this class. We need the variable and the individual. So take a minute, really do this. Take a minute, just press pause, write it down, and then come back and let's see how you did. Okay, so the implied population, as we mentioned, we need to mention the variable and the individual. So the implied population would be the mile per gallon rating, right? That's the thing we're measuring for all, because it's population, new, let's see, how did they say it? Hybrid small cars. I can tell you don't have to use this exact wording. You don't. You don't say it exactly like I did. But what we need for sure is we need something about the mile per gallons, right? We need that, and we need the individuals. The individuals are these new hybrid small cars, and we need all of them, right? All is important because it's talking about the population. So here is the variable, and here are the individuals. Okay, so when they ask you about the population or the sample, we need to mention the thing we're measuring, right? We need to mention variable and also the thing we're measuring from, which is the individuals. Okay. And then we've got one more to practice. So let's take a look here. So we've got example 5. To estimate the number of math classes college students are taking, a random sample of 1,000 students was surveyed. So what is the sample? It's the implied population. So let's kind of take a look at what's happening here. Okay, we've got, let's say there is this population. Let's say this is a pile of thousands and thousands of numbers. Right, so there's just, or maybe millions of numbers here. Each one of these numbers represents the number of math classes a college student is taking. Look at that lucky one, 4. It's like winning the lottery. So lucky. So we've just got tons and tons of numbers, and probably a lot of zeros and ones. And we just keep on going. There's millions of students. And out of this sample, so this is the entire population, we take a sample of 1,000 students. So we have 1,000 numbers here. Right, there's 1,000 numbers here. So when they ask what is the sample, it's the implied population. Well, the sample, remember what that is, that's coming out of here. That's a subset of here, right? We need to mention a variable, and we need to mention the individuals. So best thing to do, make yourself do it. Even if you don't want, press pause and try it, and then come back. Okay, so the sample is the number of math classes, right? The number of math classes. That's part of it. That's the variable, right? We always need to mention the variable. Let me get this out of here a second. So mentioning the variable. The number of math classes each of the 1,000 students is taking. So I'm just going to show you what we're doing here. We're mentioning the variable is number of math classes. That's what we're measuring. And measuring it from 1,000 students, right? So the sample, we've got the variable and the individuals, so there's the sample. So the implied population, we don't have to change too much. We're still measuring the same thing. It's still going to be the number of classes. The number of math classes. Now this time though, we don't want just the 1,000 students, we want all students. So you could say the number of math classes every student is taking. or some kind of wording like that, right? So we need number of math classes, that's what we're measuring. But this time we're measuring it from every student, not the 1,000 students, every student, or all students, something along those lines. Again, you don't have to word it exactly like me. We just need to make sure you get both of those things, the variables and the individuals. Okay, then levels of measurement. Some sad news is coming up here pretty quick here. So we have categorized data as either quantitative or qualitative. Another way to classify data is according to one of 4 levels of measurement. Okay. And these levels indicate the type of arithmetic that is appropriate for the data, but we're actually not going to cover this. Okay, when I first started teaching, I didn't cover this. And the reason is the levels of measurement, okay, this originated in psychology in 1946. Right off the bat, it was criticized pretty heavily in other disciplines other than psychology. It's just being too crude, and there are other ways to do this now that are better, not as popular, but levels of measurement is kind of dying off. So I taught it for a couple semesters and never really knew if I should, because there's a lot of stuff we need to learn about. And levels of measurement is just, the more I look into it, the more it's just criticized by pretty much everyone nowadays. So our book covers it. I'm not going to ask you about it. So the sad news is the next page, we don't need to even look at. The next page deals with levels of measurement. Example 6 is levels of measurement. We're not going to cover it. And here's the really bad news. You're going to hate to see this, I know. Skip homework problems. Number 11 and number 13. Skip these. They ask us about levels of measurement, which I'm just not going to cover. I left it in the notes because maybe someday someone will convince me that it's something we should cover, but at this point I'm not convinced. So for now, skip levels of measurement in the book unless you just want to read about it, and skip homework problems 11 and 13 in section 1.1. But you're good to go now. In section 1.1, make sure you do those homework problems. Look on the homework sheet. And, of course, if you have any questions at all, send me an email or stop by for our office hours, which for us will be online. So if you have any questions, let me know. But definitely try the homework. Try to get them done before tomorrow, because every day we'll have a new section. So, okay, get off the computer and do some homework.